Okay, so welcome everyone. Thanks Marco for the introduction. So we will be talking about SPARQL today. Um, Actually, when Marco asked me to do this presentation, which was a couple months ago, it was an easy yes for me because I did a Stardog webinar on roughly the same subject, but more on the product side. So I'm a Stardog engineer. I run Stardog query engine group. So I did that webinar explaining how to optimize SPARQL queries, which was quite Stardog specific. And I thought, okay, I will just recycle most of that material because there's a lot of useful SPARQL optimization stuff in there. But then at some point when I started actually working on this content, I realized that I want to do something a little bit different today. So instead of just talking about what the query optimizers do internally when they optimize SPARQL queries, which by the way would have been a really easy thing for me because I work 100% of my time on the query optimizer inside Stardog. Instead of that, I thought I would rather talk a little bit more about writing SPARQL queries from the user perspective, because query optimization is a lot bigger, broader term than just query optimizer, what happens inside the query engine when it runs the query. So this is not a database conference. I will not go too deep into the cutting edge optimization techniques. There will be no math on the slides. Instead, I will try to show like a typical performance problems which people experience when they run SPARQL queries, why those happen, how to recognize them, how to change your queries such that they return, such that they have the semantics which is more amenable to optimization, how to analyze query plans, and so on and so forth. So we will talk more about queries rather than optimizers internals. And before we start talking about the query optimization, one thing I wanted to, like, another disclaimer I want to put forward is that you should recognize that sometimes query optimization is just not the right thing to talk about, even though we're going to talk about it today. So when someone experiences a slow query, like you have a SPARQL query and it's slow, or you have a bunch of slow queries, people tend to think about the query optimization immediately. Oh, we need to optimize the queries. So maybe the query engine is not doing a good enough job of optimizing the queries. But it happens quite often that we should talk more about the data and less about the queries, because honestly, in many situations, given the kind of data that you have and the kind of results you want to get from your queries, it's just not realistic to expect the performance guarantees that people expect. Like if your database is powering, let's say, UI layer, and you want to show a number on the screen in less than a second, and to get to that number, you need to aggregate over billions of rows. There's nothing that you're going to do on the database side or inside your query is going to help you. That goal is not going to be met. So you should optimize the data for query performance. So there is a talk out there. So we are not going to talk about it today, but I want to highlight that as an important thing. And there is a brilliant talk out there by Julian Hyde, who is an Apache Calcite main developer. And Apache Calcite, by the way, is a framework for developing query optimizers. So this guy knows a whole lot more than me about query optimization. Yet he still delivers a brilliant talk on the data optimization, which titled exactly that: "Don't optimize my query, optimize my data." So I encourage all of you to go and pay attention. It's great. It's not about SPARQL, by the way, it's about SQL, but it doesn't matter too much. Okay, so now we move to SPARQL. So I was told by Marco that this is not a SPARQL introduction course, so I will not spend much time defining the syntax of SPARQL, what kind of things you can do with SPARQL, and so on and so forth. So I suppose most of you have written at least one SPARQL query in the past. So the syntax of SPARQL, when I put some queries on the screen, is not going to scare you too much. But I still want to talk a little bit about the semantics of SPARQL queries, what they actually mean. So SPARQL, like SQL, is a declarative query language. It has formally defined semantics. What that means is when you have a query, the specification defines what this query should, how this query, what results this query should return, like regardless of what implementation will run that query against your database. So you can reason about the behavior of queries and the properties irrespective of what tool is used to execute the query, which is great. So the way SPARQL semantics works is could be confusing to some people, but actually pretty simple. The main thing to know about the evaluation semantics of SPARQL is that it's defined in so-called bottom-up fashion. So every SPARQL query can be represented as a hierarchical structure, a tree, where at the bottom level you have nodes which match data in the graph or somehow generate data. Like there might be nodes which don't match data in the graph, like values nodes. So there could be service invocation patterns and so on. But at the bottom, there are nodes which generate data. And then that data goes from the bottom up, gets processed, gets filtered, joined until the final results are actually produced. So here we have a small example of a query. It's from one of the early benchmarks, so which I'm going to use in this talk. It was called SP2B, SPARQL Publications Benchmark. So maybe someone still remembers that. It's about the publications, their authors, editors, and the venues they're published in, like journals, proceedings, volumes, and things, stuff like that. So here you have a little query which returns articles, people who created those articles, the names of those people, but only those whose name contains the string Mary. So the way the specification defines the behavior of this query is that the first thing that happens is that the graph pattern, the so-called the basic graph pattern, which consists of 3 triple patterns here, it gets matched against the graph. So this query is going to match RDF triples, RDF patterns of the following form: articles, creators, and their names. And the specification does not say anything about how this basic graph pattern needs to be implemented by your system. It can be done by graph traversals. It can be done using joins, like in Stardog, for example. It can be done by any other means. It's defined in terms of subgraph isomorphism. So this pattern is matched against the graph. Once that's done and the results start flowing from the bottom up, the next thing which happens is the filter, which will evaluate the expression that string function contains on every name which is matched in the graph, and let only those tuples which where the name contains the string Mary to proceed. All others will be eliminated at this point. The next thing is the projection. Only values of the distinguished variables person and name will be left in the results. And after that, the duplicates will be filtered. After that, you get the final result. So it's always a bottom-up process. So it's always useful to think about SPARQL queries in terms of this bottom-up information flow. The reason I want to talk about the semantics of SPARQL so much because one thing I noticed over the years, and I've seen like many SPARQL queries over last 10 years. And the reason, by the way, I've seen all those queries is because every performance problem which is raised by a Stardog user or a Stardog customer, it comes down to me like one way or another, either immediately or indirectly through support. So I've seen a lot of queries, and yes, in many cases, we need to fix something in the optimizer in order to run that query. But in a whole lot of cases, the query just does not do what the author thinks that query should do. And the interesting correlation is that wrong queries, like the queries which do not return the results, at least on every database, which don't return the results which they're supposed to return, those queries quite often tend to be very expensive in terms of performance. They tend to be slow. So this is one example, and which I've seen at least a dozen times, where you need to query for disjoint things in the graph. So this query, the author of this query wanted to get the editors of all journals and the editors of all preceding volumes in the graph. So if you look at this query, you will see that half of the basic graph pattern matches journals and editors, and the other half matches proceedings authors and their editors. And there is no connection between those two parts of the query, which means that the query will match all combinations of journal editors and proceeding volumes editors. So if you have 1,000 volume editors and 1,000 journal editors, you are going to get a million results, a million combinations. So it's going to blow up combinatorially. And that will not be fast, no matter how you execute it, just because the query returns so many results. So this query is not optimizable. Its performance is going to be at least linear in the number of results that the query returns, and there is no easy way around that. The right way of writing this query is, of course, recognizing that you're querying for two distinct things, which are not related to each other. And if you want to combine them, you shouldn't generate every combination. You just combine them using the union. And this query is first correct and coincidentally a lot more easier to evaluate. So this query actually runs very fast on every reasonable data set and a reasonable SPARQL engine. And also, so there is almost no way how this query can be executed in some suboptimal way. Another example when something like this happens is when people update objects in their database. When people use RDF to store objects with properties, which is extremely common. It's extremely common that properties of objects will be stored as essentially outgoing edges in the graph. And this is, by the way, the only SPARQL update query which I'm going to show in the whole talk. I don't want to talk too much about SPARQL update, although SPARQL update presents some interesting performance challenges which don't exist in read-only SPARQL. But anyway, so what the author of this query wanted to do was to query documents, objects which have certain properties, creator, book title, see also links, and so on. and they wanted to update those objects. So they wanted to first delete them from the graph and then write something else instead, which seems like a reasonable thing to do. The problem here is the so-called multi-valued properties. If you imagine a document with 10 authors, and that document appears in 100 books. So the data, remember, the data can be anything. The data doesn't have to be perfect. And in the RDF world, it's more often not perfect than in the relational SQL world. So in that case, again, you're going to get combinatorial explosion. You're going to get 1,000 rows out of the where block, which will flow directly into your update templates, delete and insert. So that's going to be slow, but the worst part of it is that that will not change the semantics of the query at all, because all those combinations, they will generate duplicate triples, but the RDF storage layer will have to filter out those duplicates, because the RDF graph is a set of triples. So the query will be very slow. The query engine will spend a lot of time filtering those duplicates out. It will not be visible to the client except for the performance reasons. Instead, what should be done here is the query should just assert, the query should just return asserted edges, all asserted edges for each document, and then pass that to the delete template. There will be no combination, no combinatorial explosion here. It will use a lot less memory. It will be faster. That's the right way of doing it. And by the way, if you are writing SPARQL update queries, the best advice I can give you, which is not related to performance, but always run construct versions of the update queries first. Do dry runs. SPARQL update queries typically run within transactions. So once it runs, it's going to update your database and commit, at least in most implementations. And then if it does something which you didn't want to do, that might be difficult to go back to the previous version of the data. Okay, so my chat is gone for some reason again. Okay, so the single most important thing in the SPARQL semantics, or at least not in the SPARQL semantics, but in the SPARQL evaluation process, in my opinion, which is also the place where most of the performance problems happen, is the joins. According to the semantics, two SPARQL patterns in the same group, their results, so they generate some data and then the results are joined. So every SPARQL engine needs to compute joins at some point. They may call that differently. They may call it traversals. They may call it something else, but ultimately it's joining the data that will happen. Oh, by the way, another disclaimer, which I wanted to say in the beginning, but forgot. So I'm pretty sure that at some point in this talk, I'm going to say something which is not true for some query optimizer or some query engine out there. There are many. I know how some of them work. There's no way I can know how all of them work in all situations. So I know there are some SPARQL engine developers in this Zoom meeting. I'm pretty sure they will feel the need to correct me at some point, which is totally fine. Let me know what I got wrong. But I will try to make reasonably general statements about systems. And when I say something which is specific to Stardog, I'll try to be explicit about that. But anyway, back to joins. So if you're not familiar with SPARQL, but you're familiar with SQL and how joins work in SQL, then you might think of SPARQL joins as natural equijoins in SQL. So in SQL, joins have an explicit join condition most of the time. So you're right. In the query, it's join table A on table B on, and then you specify the condition. In SPARQL, you don't specify the join condition. Instead, all joins, they have the implicit equivalence condition on the shared variables. So if there are two patterns in a SPARQL query in the same group which share a variable, then their results are joined on values of that variable. And the easiest example how to illustrate that is values. So values is a syntactic construct in SPARQL which just allows you to specify the data inside the query. It's useful in the real world, but it's especially useful for testing because you can test a lot of stuff in SPARQL without actually any data, any real RDF data. So in this case, we have two SPARQL values patterns, two variables in each, x and y in the first, y and z in the second. The first one generates two tuples a and b and c and d, and the second generates three, b1, b2, and d3. So if you join this, the join will be on the y variable. So the y variable is the shared one, is the join key. So if you just work through that, and you see how these tuples join, and they join on y, you will see what results you get. So you take a and b tuple, you see which tuple in the second values have the b value for the y variable. You see it's the first, and then you join the tuples, you get the first result, you get the second result from the a and b tuple in the first pattern, b2 in the second, and so on and so forth. So these tuples, by the way, in SPARQL specification, they're called solutions. You can think of them as binding sets, if that's more familiar. But they are essentially mappings from variable names to values. So, a lot of SPARQL query processing is essentially generating those bags of solutions as you match the data in the graph, and then processing them as they flow up the plan. They get filtered, they get joined, duplicates are removed, they get sorted, and then eventually you get the final result. So I'm going to use the terms solution a lot in this talk, and this is what it means. So joins seem to be pretty easy concept, right? Easier than in SQL. No complicated join conditions. All natural joins. All join conditions are equality, easy. But the interesting thing, which is particularly relevant to performance, which is the reason I'm talking about it now, is what happens when a join key does not have a value. And nobody wants to talk about nulls, but sorry, we have to talk about nulls because those do cause a lot of performance problems in practice, and you need to be able to, it's useful to be able to recognize them in queries. So I don't know how many of you have seen that before, but values in SPARQL has a special keyword called undef. So what undef means is that the variable, in this case y, in this particular solution does not have a value. It has the value b in the first solution tuple, but in the second has no value. The thing I cannot stress enough is that it's not some special kind of marker value which has some special meaning. It really means no value, which is extremely important. So the reason it's important is, let's see what happens when we do the join. We get all the same results as in the first example from A and B tuple. But then when we get to the second tuple, C which has value for x and no value for y, and we start joining that with the value with the solutions from the second values pattern, then the SPARQL semantics is telling us that the join condition is satisfied for all of those combinations. So the join condition, to be more precise, the compatibility condition for SPARQL's solution is defined such that every variable which has a value if on both left and right side of the join must have the same value. But if the variable does not have a value on either side, then the join condition is automatically satisfied for that variable. And that confuses a lot of people in a lot of different ways. The reason it's important for performance is that you get new results which you didn't expect, because that C and undef tuple is all of a sudden compatible with B1, B2, and D3, and essentially any other possible solution which can come out of the second values. So in practical terms, the query results explode in very unpredictable ways. So nulls, they do cause problems in databases in general, and in SPARQL joins in particular. And then, of course, you can ask me why I should care about undef in values. Most of you probably have never seen undef in values, and that doesn't occur in most of the queries. But the reason is, it's not just the values thing. Nulls occur for many different reasons. Unbound join keys occur for many different reasons in SPARQL queries, and they do cause a lot of performance problems. And specifically, one example which happens all the time in my experience is in optionals. So you probably know, most of you, what optionals are. So they are essentially outer joins, left outer joins, if that's more familiar language to you. So they are in the query language to deal with missing data. Missing data in RDF datasets is a very ordinary situation, happens all the time. So in this example, for example, in particular, we have a query which matches people and cities where they live using the lives in predicate. For the cities, it matches the country using located in, and for the country, we want to know the name of the country. So that's the query, which works great until we have to deal with a data set where both located in and named triples can be missing in the data. And this is where people start using optionals, because that's the main reason optionals are in the standard. A lot of people will produce something like this at that point. So they just put patterns which can be missing, which can correspond to missing data in the graph. They put those in the optional clauses. And at this point, we have a problem. The reason we have a problem, to understand why we have a problem here, we need to look at the SPARQL algebra. And the algebra is essentially the representation of the query, how it's defined in the specification. So some advertisement here, like I use the sparkl.org resource daily, essentially. It's not associated with Stardog in any possible way, so I feel no shame advertising here. It's a collection of online tools which help you see the query algebras and even run queries on some small data sets or even on empty data sets. It's tremendously useful when you want to double check your understanding of the query, what it means. You can use that and look at the algebra. So in this case, it would tell us something like this, how this query is represented. And remember, the evaluation is bottom up. Well, this tree is drawn from left to right. So when I say bottom up, you should hear like right to left. So the 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 bottom nodes are the BGPs. Well, BGP is yes. So the BGP patterns. Person lives in the city, and the city located in the country, and they are in the left join, which means the country variable can be unbound, can be not bound to a value, but may not have a value once that left join is evaluated, right? And that happens before it's joined with the name pattern. And by the way, this is the order of those optionals is fixed. You cannot swap them. So the first optional join doesn't present any performance problem. The join variable should be bound on both left and right. But once the results of the first of the nested outer join are computed, then the country variable may be unbound, and it's a join key between the nested left join and the BGP. So what happens in the practical terms is that for every person who lives in a city without a located in triple, the query will return all countries. So the results will explode, and that's almost, I feel very confident that this is not what the author of the query wanted at this point. It will also be a performance problem, but first it will be correctness problem. And as I said before, incorrect queries are quite often very expensive, and this is another example. So maybe this is not the case in the data at the time the query was written, but it can always happen later unless the query is updated under some very strict integrity constraints. But I'm not going to go there. So being able to recognize this kind of problems is pretty important. They often show in the query plan, and we'll talk about query plans later. But if the system provides insights in the query evaluation, it will give you a hint that there is a performance problem like that in the query plan. A better way of writing this query would be to push the other optional inside the first one, use a nested optional. In this case, the join on the country will happen before the outer optional is joined with the lives in, and there will be no results explosion like that. There might still be a performance issue depending on how the query engine decided to go about evaluating this query. But the important thing is that this query is optimizable. It produces the reasonable number of results, and the query engine has a chance of generating a reasonable plan for it. While for the previous query, if it explodes, it explodes. There's no way around that. Okay, so I might need to speed up a little bit. So just continue talking about joins. So there are multiple ways how people go about matching data in the graph. So some people, for example, if you want to query for all people living in some city and to find the country for those cities, you can naturally write a SPARQL pattern like at the top. But it's also quite common for SPARQL users to use different variables for the city and then just use a filter to sort of equate them somewhere else in the query. And these are often considered two ways of achieving the same thing, especially if the query is auto-generated by a program for some reason. The bottom part is very popular. I see this all the time. And a lot of people feel very comfortable doing it. And it's true that in this example, this query should return the same results, but it's not always the case, unfortunately. It can also be a performance problem. So the issue number one here is that if you use different variables, which you then equate using a filter, you're relying on the optimizer being able to recognize that these variables are actually should have the same value in every result to this query, which seems quite obvious in this example, but it's not obvious in general because the filters can be complex. They can have very complex expressions, nested expressions, and the analysis of those expressions may not be trivial. The query might have nested graph patterns. So, and then the query optimizer will have to recognize that, okay, there's an equality filter in one pattern, but it should be enforced for BGP somewhere in the nested patterns, and this can get non-trivial very quickly. And then there are, of course, filters and optionals, and they have special semantics in SPARQL, and they behave a little bit differently. So my advice usually to not use that filtering approach if you wanna query for, if you know that two variables should have the same values, just use a single variable. It always helps the optimizer. And the issue number two is that this filtering approach may even return different results from the join if the variables bind to something, to RDF terms, literals, which might be equal but not identical, which is particularly true for numbers. You can have equal numbers which are different RDF terms. And when that happens, the optimizer might just fail to rewrite this into a join because it doesn't know what kind of data it's going to run that query on. And strictly speaking, according to SPARQL semantics, you cannot, in this case, you cannot rename company by employer or employer by company and run this query. You can only do that if the query engine understands that the range of the ounce property and the range of the works at property is RDF terms for which equality behaves the same as identity. If those are like iris or strings, but not numbers. And in general, query engines don't know that unless there are some hidden assumptions. So my advice, rename variables in your queries. Don't rely on filters. And the single most important thing I want to talk about today, I'm pretty late, is the order of joins. Because the order of joins is such a critical optimization, and not just at SPARQL, and in essentially every first order query language. It's not the only thing that the query optimizers do, so it's entirely possible that your query optimizer got the join order correct, but the query is still slow for other reasons. But in many cases, if the query optimizer got the join order wrong, then nothing else is going to make that query fast. So this is almost always the case in my experience, at least in non-trivial queries in large data sets. So the order of joins is absolutely critical. And SPARQL engines at this point are pretty good at reordering inner joins. So if you have a collection of patterns in the same scope and they are joined, there are no optionals around, then the query optimizer will try to compute the optimal join order, decide in which order patterns need to be joined. There's no guarantee that the result will be the optimal join order, but pretty much every SPARQL optimizer will try that. And this problem is very well studied. It's a classical query optimization problem. Once you've got optionals into the picture, all of that changes. Like it's amazing how much of that changes. if you have a sequence of inner joins and outer joins in your query, and this is not true about SPARQL, it's true about SQL as well, then it's hugely more difficult to come up with a sequence which is most efficient to evaluate. Which in SPARQL case, in simple terms, means that optionals are quite often executed as is in the position in the query where they are specified by the user, which may not be optimal. And that's so I know a lot of people are frustrated by that, and I will try to explain why that happens. So the thing about the join order optimization for inner joins is that it's a hard problem. It's an NP hard. It has the huge search space. The search space is essentially all permutations, right? But for inner join, that search space is easily structured. So every permutation is the valid join order, because join as a relational operator, it's commutative and associative. You can swap the operators. You can set the parentheses in any way you want. The query will produce the same results. And that's hugely important. That means optimizers can enumerate those options, maybe cut the search space, but it becomes like a classical search problem. And at this point, we're pretty good at optimized search when the search space is well defined. The problem with optionals is that it's not that the search space is bigger or somehow harder. It's that it becomes much harder to define. It becomes much more difficult to generate sequences which preserve the semantics of the original query, because many of the properties of which are true for inner joins or sequences of inner joins, they're not true for sequences which contain optional joins or outer joins in general. So the first property which fails is commutativity. You cannot, like where like A and B are SPARQL patterns here. If A optional B is not the same as B optional A, you cannot just swap them. That should be obvious, I hope. A more interesting question is when you have a sequence, so you have an optional join of B optional C, and then you join it with A. Can you swap, can you essentially remove the parentheses and say, okay, I will do inner join of A and B, and then optional, and then outer join C. So in SPARQL, in practical terms, basically asks, can you move your optional up and down the query? And surprisingly, to some, the answer is no. You cannot do that in general. And it's not difficult to come up with a counterexample for that. So by the way, this example, I specifically used values, not real SPARQL patterns, not BGPs or something which requires data, because you can enter the SPARQL pattern to sparql.org. There is, I believe, Fuseki engine behind it. And you can see that this query with optional in the middle returns one result, x equals d, y equals e. If you move the second values up, or equivalently you move optional down, the results will be different. So this is not a valid optimization for this query and many other queries. So I will not go through the details why that fails. I mean, you'll have the slides, you can do it on your own. You can double check that, you don't have to believe me. But it's the reason that optionals, SPARQL query engines, at least those I have experience with, they deal with optionals a lot more carefully than with inner joins. So don't rely on them doing a lot of things with your optionals. Place your optionals wisely. Think where those optionals should be in the query. Remember that optionals, they never decrease the number of results matched by the patterns before them, right? Because if the join fails for some solution on the left, that solution on the left will still be in the results. It's just the variables which occur inside the optionals, they will not have values, but the result will still be returned. So this is one area where SQL optimizers have a lot of advantage compared to SPARQL optimizers. One of the well-studied optimization in the SQL world is rewriting outer joins into inner joins. For example, if the optimizer knows that there are foreign key constraints, so that there must be rows in the linked table, they can rewrite outer join into inner join, and the results will be preserved. SPARQL engines, again, I could be wrong, but as far as I know, none of them does stuff like that unless they operate under some assumptions which are not in the spec. And this is one area which needs advancement in the future, I believe. And there are some publications which will help, which specifically talk about enumerating all valid sequences of inner and outer joins in your query, so the query engine can decide which of them is more optimal. So the canonical abstraction for outer join optimization, great paper, highly non-trivial algorithm, which all it does, it generates all valid sequences of inner and outer joins for the given query, without even considering how to decide which of them is faster. It only defines the search space, but doesn't explore it. Okay, I really don't want to talk a lot about SPARQL federation. And I know a lot of people are excited about SPARQL federation, especially people working with open data and linked open data on the web. People love Wikidata. I must confess, I don't have a lot of experience with federation. Stardog is mostly used for enterprise data, so the service invocations using public endpoints is not exactly what we face in many cases. But what you need to remember when you have services and thinking about performance of your queries is that they behave, they are just SPARQL patterns. So they are executed and their results are joined with the rest of the query, just like any other pattern. But they do present some unique challenges. So namely, the query engine has no idea what kind of data is hidden behind that endpoint. So there's no selectivity statistics generally available. Endpoints are unreliable, so the cost function for invoking services have to account for that somehow, but it's unclear how fast that will actually be. And the data transmission ingestion costs, all of that makes it harder. So one common thing which you could expect from many SPARQL optimizers when they run queries with services is that they will try to constrain service invocations by local bindings. So for example, if you query people working at Stardog, 10 years ago there were not many people, but you want to use Wikidata to join that information with all people living in New York City, you don't want to dispatch that unconstrained query for all inhabitants of New York City to Wikidata. Most likely Wikidata will not be super happy about that. So instead, what query engines will try to happen, they will try to find the local pattern which joins with the service, evaluate that local pattern first, get its result, push them into the values bindings, and then push those bindings into the service invocation. And you should be able to read query plans to see whether that happened or didn't happen. And you should try, if you see that it doesn't happen, maybe you should try to help the query optimizer to see that there is actually a local pattern for the same variable. Place them close, at least in the same graph pattern as the service, not somewhere far away in the query where it's difficult to find. Yeah, I'm not gonna finish all of that, but at least we should talk about query plans a little bit. So at some point, after you've got a slow query, you looked at the query, you understand the semantics, you looked at the query plan and the algebra, you convinced yourself that the query is correct. It's supposed to do the right thing. It's just slow. And the question is, okay, what's next? What's the next step? At this point, the most important thing is try to guess as little as possible, and instead learn to read the query plan provided by your system. Things quite often go very wrong at this point, and I've seen a lot of examples how intuition fails. So one typical intuition failure here is, so the story typically goes something like this. I had a query which was great, running fast. Then I added one pattern, like I wanted labels instead of IRIs. I put it somewhere in the query, and then it's very slow. Why is it very slow? It should be just one extra join, right? So what happened? And there's also the inverse version of the same intuition failure, which is something like, I had a query which was very slow, so I started pulling things out of the query until it's fast. And so it's those things which I removed from the query, they have to be responsible for the bad behavior, for the poor performance. Both of these things are false in general, and in Stardog case in particular. And the local changes which you do to the query, they do not mean local changes in the evaluation plan. You might change a little thing in your query. SPARQL query engine does not guarantee that there will be similarly local changes in the evaluation plan. It could completely change the way how it runs the query for various reasons, for good reasons and bad reasons. So just briefly, I need Stardog query plans to illustrate this point. Stardog is a pretty classical query engine in terms of the evaluation model, which it follows, the so-called Volcano model. It's been known since late 80s, I think. Götz Greffe and his seminal work on first system, I think was called Exodus, and then Cascades, which is still a basis of many query optimizers at Microsoft. The idea of the architecture is basically every bit of the query plan corresponds to some executable operator, and those generate results, and the parent operators, they pull results from the child operator. So it's a pull-based model. So if you remember that badly written query for all journals and all journal editors, all preceding editors, which blows up because of the Cartesian product. So let's see how it looks, how the query plan looks. So the first thing which Stardog would do, it would evaluate the BGP against the data. And every triple pattern in the Stardog case will be an index scan against some index. So four triple patterns in the BGP, 4 index scans. They'll be joined using the merge join algorithm in this case. Those will be joined, and then the results will be projected. And at this point, Stardog will tell you that once we've got the proceedings editors and the journal editors, and we need to join those, there is no shared variable, so it's going to be a nested loop join, and that empty space in the parentheses means no join key. So at this point, if you know how to read Stardog query plans, it should be a big red flag for you. That because the Cartesian product happens there, there's no join condition. Okay, so the last thing I probably say at this point is how performance problems happen when they are not related to any kind of combinatorial explosion inside the query. So the most efficient query execution is streaming. So the scans, they match some data, or the BGPs, they match some data in the graph, they generate some results. Those results, they get processed even before all of the results are matched in the graph. They are immediately processed, filtered, joined, they start moving up the pipeline. the final results after the projection, they ship to the client while the rest of the query is still being processed. So the results are never accumulated in memory somewhere. When that works like that, the query is going to be very efficient, unless it generates a tremendous number of results, which is not should not happen for reasonably written queries. And the example of that evaluation, streaming evaluation, would be the merge join algorithm, which is by far the fastest join algorithm one can ever imagine. I don't think there's anything faster than the merge join. It does require that the inputs are sorted by the shared variable, the join key. So for example, in this case, you have two scans, two patterns, authors and journals and editors. If both of them are sorted by the values of the journal variable, then the join will go like this. So the first relation is scanned, and for the value of the join variable here, the first one is the Journal of AI Research. We can do the binary search inside the second relation, utilizing the fact that it's sorted by the join key. So we can skip a whole lot of data in the graph, which has journals which are less than lexicographically than the journal of the AI research. We don't even have to load them from storage if the storage supports that. So we find the first one for the Journal of AI. We immediately generate the result. So that result can go up the pipeline or even go to the client if that's final. And then we do the same on the second relation. The second is the Journal of ML Research. We seek to that row in the first relation. Again, binary search, very efficient, skips a lot of data, and that goes to the client again. And that goes on in that zigzag fashion until all results are computed. So nothing is accumulated in memory. The results are produced as soon as they are generated. So that's great. If that works like that, there's no performance problem whatsoever. That breaks sometimes. Unfortunately, in many cases, you cannot answer the whole query like that for reasons like hash joins. So sometimes data is not sorted the way you want it to be sorted, and then they need to be accumulated in memory, either in a hash table, or it needs to be sorted, or maybe there is an aggregation in the query, which cannot be done in a streaming way or something like that. So the huge difference between the hash join from the merge join is that we need to put the whole right relation or left relation, whatever, into the hash table before we produce even the first result of the join, at least in the classical version of the hash join algorithm. So while the whole relation is hashed, nothing else is happening, at least in those parts of the query relation which expect the result, which need the results of this join. And only after that we can iterate over the other relation linearly and probe in the hash table and then produce the results. So the reason it's called the pipeline breaker is because there is a delay while the hash table is being built, and the pipeline doesn't do anything useful usually at that moment. So a lot of performance analysis and performance problem and performance debugging comes down to finding pipeline breakers in the plan, or the bad join orders with like hash joins, which result in those pipeline breakers having place. So if you just can do that thing alone, like finding pipeline breakers and checking how bad they actually are, like how big are those hash tables and how big is the data which is being sorted, that is already almost enough to diagnose like 80% of all performance problems in many SPARQL queries. So this is huge. This is like the single most important query analysis skill in SPARQL, I would say, just finding those in the query plan. At this point, I will probably stop because the rest of the slides which I have, like I can talk about engine specific tools and the query hints, but I'm over time and we need time for questions. So I will try to stop here and actually start taking questions. And if we still have time after that, I can talk more about these things.
Very good. Thank you, Pavel. Well done. Let's.
Yeah, I apologize for not actually. I was actually not seeing the questions while I was talking. So the
Yeah,
crazy thing is that
don't
this
don't.
Slack
Can you
chat
make me
didn't.
the organizer, please?
Yeah, sure. Let me just find your. Okay, oh, there we go. No, make. Yeah, just made it a host.
Excellent. Very good. Well, it's a lot of stuff. I think it's a nice fit to the presentation that is already online about SPARQL query optimization. I think it's a good time to take some questions now from the
Sure.
audience. Please raise your hand. I would like to thank all the participants. Actually, they were really good. They helped me a lot to make this a smooth presentation here. So please raise your hand if you have a question. I also looked through the chat log. I noticed that I think quite at the beginning, someone asked the question whether or not we actually need to worry about optimization. Isn't that something the computer could do by itself? Isn't the software?
Let me go through the questions. So I'll try to. Okay. So I think I can just go like in the chronological order, if that's okay.
Okay, yeah, go ahead.
All right. So doesn't this idea of data optimization leads automatically to the old ETL stuff? We can optimize data as we want. We don't want to do it anymore. Yes. So this is valid point. Absolutely. So a part of the appeal of RDF and SPARQL is that your data, your schema is flexible. You can put all kinds of diverse heterogeneous data and then query it. That's true, and this should not be taken away. But it does have, so there is a little bit of a conflict here. The more structured your data is, the easier it is to query, and the less structured your data is, the more difficult it is to query. And I don't think there is any way around that. So you need to find the right balance for each system and each application. And RDF does not mean schemaless. It doesn't mean that it doesn't have a schema, which I think it's presented like that occasionally, and I think it's a kind of a wrong way of talking about RDF. At least in the enterprise data world, it's in my view, it's more important that the schema can be changed flexibly at any point, but it doesn't mean that you should not design your schema with query performance in mind. So, and we do have customers which maintain things like partially aggregated values somewhere in the graph, because those values need to be available to the applications using very low latency queries, which physically cannot do that at runtime. So those things happen, and it's just reality. So I'm not familiar with linear algebra joining. Yeah, honestly, not sure. I've personally never seen anything faster than merge join for joining large amounts of data, but I will take a look.
Could you repeat the question when you read that?
Oh, yes. Okay. So the linear algebra joining, could it be faster in main cases than merge join, especially with the tool called GraphBlast? And I'm just saying, not familiar with GraphBlast. I'll take a look later. Yeah, in my experience, nothing beats merge join, well implemented merge join. So shackle question, how shackle might be used as a hint to the optimizer. This was briefly mentioned with reference to the optimizer not knowing whether a filter A equals B or to join URIs. So this is a great question, and I love this question. And actually, it's perfectly valid to design, to make the assumptions which are enforced in the shackle constraints available to the query optimizer. So shackle, for those of you who don't know, is the W3C standards for validating, for enforcing integrity constraints on the data. So you can declaratively specify the shape of your data, and particularly what should be the no how the RDF terms in the range of a particular property or in the domain in particular property should look like, whether they should be IRIs or literals, and if literals, what the data types should be. So essentially, it's a rich source of schema information. And if that information is available to the query optimizer, then the query optimizer can do a whole lot more than without the schema. The schema is a hugely important source of information to the optimizer. The downside of that, of course, is that if your system does let the data which does not conform to your shackle schema into the database, and the query optimizer doesn't know that, so it operates under the assumption that the data does conform to the schema, then the query results may not be correct, which may or may not be okay for your particular application. You may care about the bad data which doesn't conform to the schema, or maybe you don't. But this, I don't know which query optimizers do that at this point, but I know the SPARQL systems which take query hints, which explicitly say that, okay, the range of this property is the IRIs and not literals. So if I'm not mistaken, there is a blaze graph hint which you can denote that the predicate is safe, if that's the right term, and then the optimizer will use that. And by the way, the blaze graph, the Wikidata query service page has a pretty nice write-up about the query optimization hints and what you should or should not do. It's linked from the Wikidata query service page. I encourage you to read that.
Yeah, and I think we also want to mention the names of the people that put these questions forward. This was by Robin Gower, and
yeah,
now,
that was Robin Gower, right?
And now the next one.
Do I have any recommendation of good papers about SPARQL query optimization to read? Yes, I should have prepared an answer to this question, but okay. My favorite paper would be by Thomas Neumann on one of the earliest SPARQL systems called RDF3X, which actually had a lot of influence on a lot of SPARQL engines developed later. I don't remember the exact title. I will have to Google it, but if you just Google Thomas Neumann and RDF3X, you will find it. It's very widely cited. It discusses a lot of things, a lot of the optimization strategies like sideways information passing. It talks a lot about cardinality estimations. Like pretty much every concept which you see there is still in use in some form. And it's great. That was the question by Thomas Tanon. Okay, so then there is a question by Ravinder Singh. Assuming I have done optimizations for where clause, any ideas on large count queries or reporting with large count queries? I'm not exactly sure I understand the question. Like maybe you can uh, elaborate a little bit while I move to the next question by Donnie Winston. Can you speak to the issue of inference and how query optimizing comes into play? For example, materializing all inferences versus searching for them during a query. Right, that's a good one. So in general, there are two distinct, well, principally distinct approaches to reasoning when it comes to SPARQL. And of course, there are variations of like the mixtures of both. Like the first approach is to materialize all inference in the data and essentially run the query, SPARQL query as is, because it would know that every fact which follows from the triples in the data will also be in the data as a triple or collection of triples. In that case, the query engine doesn't need to do any extra work. It will just run the query as is. And the other approach is not materialize inferences, but do reasoning and query time. And that can be done in different ways. Stardog, for example, does that using query rewriting. So the idea is to take the query, the SPARQL query, to take the ontology, an owl ontology, and rewrite your SPARQL query into another one which encodes the semantics of those terms which appear in the query, essentially. So if you have in the query that give me all instances of class A, and your ontology says that A is a subclass of B, then the query will look something like, give me all instances of A. No, if you're, I'm sorry, if your ontology says the B is a subclass of A, and you're asking for all instances of A, then the query would look like, give me all instances of A and all instances of B, because that's what your schema tells me, that every instance of B is also an instance of A. So the query will be bigger. Unfortunately, it might be non-polynomially bigger, depending on your ontology language. And the query optimizer will have to deal with that. So it will have to handle that extra complexity when it optimizes the query. So you will pay that cost at runtime. And then, of course, there are combinations of two approaches when some data is materialized but not other. In that case, the optimizer will have to figure out what it needs to rewrite in the query, what it doesn't need to rewrite in the query. This question, by the way, gets a lot more difficult when your query uses any kind of recursion, or there is recursion in your ontology axioms. And by recursion, I mean things like property chains and all, or transitive properties. You can translate some of them into SPARQL property paths, but not all of them. So it becomes non-trivial. Okay. It's embarrassing. I'm not sure how to pronounce the name. Is it Jindrich? Jindrich? Like, I know this guy online, and I'm still not sure how to pronounce the name. Like, I apologize for that. But the question is there something you can recommend to query authors for self-join optimization, or is it only possible for query engine developers? I'm not entirely sure what you mean by self-join. Is it join on the subject variable, like a star-shaped join, or
maybe we move that question to the open session afterwards if you're not sure.
Yeah. Okay. Cool. The next one from AK. I have a large data set that uses query. We use limit and offset to keep the result set small, but almost always there is the sort order that they want. This combination of a big query space and sorting hurts us. There are techniques, design patterns, or other things I should be thinking about to help query performance. Yes, another good question. It's a pain point. Essentially, this question comes up a lot in my experience when applications need some kind of pagination behavior. So they want to scroll the query results. So they want to get the first page, they want to get the second page, and so on and so forth. And the expectation typically is that so people expect some kind of cursor behavior, which is what major SQL databases provide. So like most of the work is done when you get the first page, but then you have some kind of cursor and you get the second page faster. This is not always the case in SPARQL, unfortunately. So you have to work with you have to figure out whether your system supports that cursor-like performance or not. Because if it doesn't do it, then there is a good chance that when you do the second query for the second page using the offset, that it will repeat the work which it did before, except that it will filter the results of the first page. If that's the behavior which your system implements, then you should probably not implement pagination using limit and offset, because from the performance point of view, it will not work very well. Omar Khan, any tips on handling property paths of arbitrary length, many levels, constructed many optional, sometimes star causes performance challenges? Yeah, I love this question. Unfortunately, I didn't get to the slide where I was talking about property paths. I can spend the whole hour just about on property paths. So you're totally right that the star causes performance challenges. The reason for that is the star is dangerous. Its semantics is explosive. It includes the so-called zero-length path. So if you have a pattern like X RDFS subclass of star Y and nothing else in the query, then you will get at least as many results as there are nodes in your graph. So the zero length paths are just nodes. And this is something which a whole lot of people don't realize immediately, is that the property path stars, the matches every single node in the graph, including literals, including nodes which can never occur as subjects in triples. And in practice, what that means is that if you want to use star, first of all, think about it. The second, there should be something else which constrains either the start variable or the end variable in that pattern. It should be either the constant or another pattern in the query. So the typical example would be RDF RDF type slash RDF subclass of star. In that case, it will not explode because you will first get bindings for the RDF type, and for those results, you would get paths. So thanks a lot to Greg for providing pointer to the RDF3X. Yes, exactly the paper. There are a bunch of follow-up papers. There's another one called, I believe, something about cardinality estimations, which mentions characteristic sets. It's a great one, also hugely influential. And by the way, you should follow Thomas Neumann, not just for SPARQL star stuff, but in general, if you're interested in databases and the query optimization. He's probably, I would say, in top 3 of database researchers in the world right now. Anyway, going forward, can moving data, again, the question from Omar Khan, can moving data to named graphs help navigating many level relations? And how would from and from named help with this? Yes, it can help. From and from named, they define the data, the part of your RDF graph that the query will run against, or parts of the query will run against. If the query engine supports that well, it can restrict the amount of data that like BGPs will be evaluated against. Those, so the data set may not just be specified using from and from named, it can also be specified externally to the query using the SPARQL protocol. Generally, it's a good thing to do, especially given that if you don't specify your data set, then SPARQL query systems may even disagree on what is the data that the query should run on. Some systems will run it over the default graph. some systems will run it over the all graphs. Some people will run that over all named graphs. So there are blog posts on that. So it's always a good idea to be clear what the data set, what data set the query runs against. How Stardog compared to Virtuoso? So yeah, so Virtuoso, I'm not sure how much I should talk about that. So Virtuoso is a great system, by the way. It in terms of performance, I really think quite highly of Virtuoso. It's a difficult system to compete with, but also the focus of Stardog is different from Virtuoso. So most of Stardog is not just a SPARQL engine; it's the other part of the knowledge graph platform, which is like, for example, data virtualization and reasoning. So we spend a lot of time
also
on
want to
that.
go into the open session, so maybe we work on the last two questions.
Okay. Okay. So I will just say that it's comparable. I know queries which Stardog runs faster, and I totally know queries which Virtuoso runs faster. How mature? Look, another question by Andreas. How mature would you call SPARQL query optimizers compared to most mature SQL query optimizers like Teradata or Oracle on maturity scale from 1 to 10? I would prefer to not assign it a number, and they are not as mature. So there was a talk recently on by Microsoft research group on the Cascades optimizer, which has been evolving since the middle 90s. So I will just give you some numbers. So the guy when the guy was talking about the query optimization rules which they have in the system, they mentioned they have around 400 for the state-of-the-art Microsoft SQL Server modern version, 400 rules. In Stardog, we have, at this point, I would say about 40, like an order of magnitude difference, if that tells you something. But it's also wrong to talk about, like, use a single number as a maturity, because some parts of SPARQL query optimizers are substantially more mature than others. Like in terms of the inner join orders, I don't feel like SPARQL query optimizers are that bad compared to SQL. Pretty much every optimization technique for join ordering which has been developed for SQL is applicable to SPARQL and has been used by someone at some point. But when we get to other places like outer joins, the gap is higher. So it's hard to say in general. Okay, self-join via subject when you have big star-shaped patterns. I would say, at least for Stardog, will always consider running those joins like together, unless it has a compelling reason to split them up. And so if you know that the optimizer should split them up, maybe you should put them into different scopes using like subqueries, for example. But normally I would expect most systems to run self-joins together, especially given that cardinality estimations for self-joins are usually easier to get correctly than for joins in general. And finally, there is another question by Robin Gower. Is there is lexicographic sorting of URIs and merge joins? Do long URIs slow the engine down? It's not that simple. Many systems, including Stardog, they don't do joins over actual RDF terms, which you have in the data. So once Stardog runs joins, it does not compare URIs lexicographically. What happens instead, the data is encoded, and every RDF term is represented using a 64-bit integer value. And the joins operate on those numbers because it's a whole lot faster. And from that point of view, the length of your URIs does not matter at all until there is something in the query which needs to see the URIs, like you will evaluate the filter function, like constrain contains, or once you start shipping those results to the client. In that case, the data is, of course, de-encoded, and those long URIs will play some role. But but the relationship is not straightforward between the length of your terms and the query performance. All right, so I think I got through the questions, so we can
very
move
good.
to the discussion.
Pavel, thank you very much for the presentation. This was great. Thank you to all the participants. We are now going off the record. We're now stopping the recording. And let me do that. Stop the live stream.